We'll get. I think everyone's here. We will be getting started at 1, so a little more time. So we are Deimos II, and this is our preliminary design review for the fall of 2020. So essentially, what we are going to be covering today is our PDR summary, our propulsions, our aerospace, our software dev and system integration, and also our projected project activity, which will cover our budget and then also timeline. So essentially, here is how this is how the whole team is essentially structured. I am Jonathan Martini, and I am the project manager. Our integrations lead is James Stewart. Our structures lead is Colton Williams. Our propulsions lead is Simran Dohu. And then for our 2 avionic sub teams, our ground station control lead is Jonathan Stuicker, and then our flight systems is Joshua Vonnersek. So one of the things that we have done is that we have created a GitHub organization to hold essentially all of our models and then all of our code base for the whole club. And really, we are the first team to basically use it, pioneering this tech for the whole club, which we'll be using. And so some of our team goals for this team is to essentially build a foundation for future solids teams to essentially expedite the prototyping and then also the development of future teams. And some of these goals are to essentially make a solid code base for everyone to use. One of the biggest problems I personally saw with basically how stuff was being run was that code was not being it was hard to get it between one person and then the next team. We've lost a bit of code with the that was like in C++ and from previous teams, and so that's why we made that's why we're using GitHub. And then also our goal is to essentially minimize costs for the whole team. So we reused almost all of our hardware from past teams, and that has made it extremely cheap for us. So and then we are also trying to work on building a base flight systems and ground station control system for future teams to use. And finally, our main goal is to compete in Spaceport America Cup 2021. So I'll give it off to Colton.
Right. So beyond just the team goals we have for this year, we have a number of mission objectives for the launch itself. The first of which being to launch an apogee of a minimum of 10,000 feet. Now this is just a part of the IRAC competition that we're a part of. This was their first height threshold for their different competition teams, and it's the one we decided to go with. Now, much of what we're planning to do for this flight has to do with avionics. We're a very avionics-oriented team. We'll get more into the specifics later in the presentation, but to just kind of outline what we actually want our avionics systems to do. The first main big thing that we want this to do is to transmit flight data from the rocket while it's flying to the ground control station. Now, we want to do this for a number of reasons. The first of which being, we've tested the radio system on past teams, and we want to try and integrate it into a competition-grade rocket, as well as for some of the ground control station projects. The first of which being calculating or writing a simulation software that can estimate what the possible trajectories of our rocket are going to be. kind of a common trend with our club in the past is losing rockets after deploying them to high altitudes. We figure if we can use data to more accurately predict where they're going to land, we'll have a better chance of recovery and recovering all of this hardware that we're putting in. Just kind of a more basic mission objective is to deploy the recovery system and payload. We will be having a deployable payload, which we'll get to in a couple of slides as well. But since that's deploying and the rocket needs to be recovered as well, that'll be the last objective of our team.
For the launch vehicle summary, we'll be using a AIM-class motor to have enough thrust to get the rocket above 10,000 feet. In the body tube, we will have a flight computer and a telemetry system to record flight data and atmospheric data. And our payload will be a bioatmospheric data collection system. This will capture and record data on samples of air at different elevations. Now the rocket, along with the payload, will be recovered with a dual deployment recovery system, ensuring safe recovery. And the characteristics of this rocket are an expected apogee of 10,362 feet with a maximum velocity of 734 feet per second and a maximum acceleration of 188 feet per second squared.
To get a little more into the avionics system, starting with flight systems, we'll be using the same standard BeagleBone Black that we've used on past teams. It's tried and true. It's cheap. We already had one. And like John was saying before, pretty much all of the materials we're using have been taken from past teams, which has allowed us to essentially become a very cost-effective launch vehicle for this competition. So some of the benefits of the BeagleBone Black, much of the Python scripting and stuff that we've written in the past is easily used and converted to the sensors we're using this year. Many of the sensors and essentially most of the avionics system that we used for our Phobos team last year that we had designed, shown here, will actually be being used again within this rocket. We will also be automatically logging all of the data from the sensors within the BeagleBone, as well as serializing it for the radio. In terms of what sensor data we'll actually be collecting, right now we're just using an IMU, which will be able to read accelerations in 6 degrees of freedom, as well as an altimeter to measure both the pressure or the ambient air pressure, as well as the height of the rocket. Both of these are incredibly useful when sending over the ZoomLink Z9C radio to the ground station, as this data will be directly fed into the ground station's program. Now the ZoomLink radio itself is a military grade radio that we were gifted a number of years ago by the ZoomLink company. And it's military grade, which means it has up to a 60-mile range. So this system is easily expandable into the future. Should ARA in the future wish to try and send rockets even higher, this should have no problem transmitting any relevant data between a ground station and the rocket. And then to quickly summarize what our payload is going to be, it's a deployable bioatmospheric data collection system. So essentially what we want to do is to measure how well life can survive at different levels of the atmosphere. We've been working closely with a man by the name of Dr. Thomas, who teaches at Lyon University. He is a biology professor who also has an interest in model rocketry, and we managed to find his system depicted here on YouTube. We got into contact with him, and we've been working very closely to figure out the best possible ways to collect air samples at multiple heights. The most efficient way of doing this is actually to create a kind of atmospheric probe. Now, at apogee at 10,000 feet, we're planning on ejecting our payload along with the drogue. So as the body tubes come apart to deploy the drogue, we'll be shooting out our payload in some capacity. Now, it'll have its own parachute system and will gradually float down throughout the atmosphere so we can take accurate samplings at 10,000 feet, 5,000 feet, and finally ground level. We'll also be designing a custom flow-through sensor array to measure the ambient conditions that any potential microbes may have been living in. Excuse me. This is a very cheap solution for analyzing extreme environments. It's not every day you get to take readings at 10,000 feet. So we're really trying to make sure we get as much data as possible for any researchers here on campus or for Dr. Thomas as well. The build shown right is only $30. All of these parts are easily sourced from eBay for $4 to $10 a pop. It's very lightweight, so we can fit multiple of these within a fairly small volume, and it's easily expandable as well, since all of them can be strapped together. Any sensors we'll be using is very easily integrated with all the existing code we have. It's as simple as just downloading a new sensor library and integrating it with the existing universal code we've already created.
All right. Can everyone hear me? Cool. So for our process for choosing a motor, we used a student-written code to do one-dimensional characterization of the flight, basically analyzing one-dimensional forces, thrust, drag, to get some numbers so we could quickly choose a motor without having the rest of our rocket finalized. And so our first graph, it's measuring max altitude to the mass of the rocket without motor. And you'll see two standouts, I'll call them green and blue. And so those were our number twos. We're like, okay, cool. Next, please, John. And then once we look at our max Mach number, we see some differentiation between the two motors. Green has we get into a supersonic transonic area with our green motor. And it's a cause for concern, and it's just overall bad. And so we're looking at blue and we're like, okay, this is very cool. Next one, John, please. And you see the same with our max dynamic pressure, where it becomes a factor of 4 between the blue motor and the green motor. And so this sort of this is how we our process for choosing our motor. Granted, the written code has some issues, like it assumes constant thrust and a constant coefficient of drag, but overall, this is a great solution for finding our cost motor to use for a rocket. And go ahead, Sarah.
All right, so after running a lot of simulations on OpenRocket, we narrowed down to 5 possible motors that we use to generate the plots for our MATLAB code that can A, take us to 10,000 feet, and B, make sure that our rocket is not tail heavy and maintains the stability that we need. So based off on the liftoff thrust to weight ratio, the total mass, the total impulse of the motor, we ended up choosing our M-class motor M795 from Cicerone. I would like to go over some couple of benefits that this motor has in the context of this year's Deimos team. So firstly, it's a reloadable motor, so our team members can have more hands-on experience assembling the motor, since this year our responsibilities have been limited by using a COTS motor. This motor also comes with a motor case and ignition system, so it cuts down on the cost, since we're trying to limit the budget for this year. And it also uses the moon burner propellant, which has a great thrust profile. The thrust profile of a classic moon burner propellant grain results in a maximum thrust at ignition, followed by a fully regressive thrust profile that minimizes the dynamic flight stresses on our rocket. So as you can see here, the average thrust generated by a motor is around 794 newtons and has a total impulse of around 10,000 newton seconds. The burn time of our motor will be around 13 seconds. Additionally, our motor parameters and the total mass of our rocket gives us an initial thrust to weight ratio of 4.75. This ratio is slightly lower than our ideal ratio of 5 or more than 5. Referencing from sources like the High Power Rocketry book by Mark Canepa, the 5-to-1 ratio should be maintained in order to have a stable vertical flight. So we will be looking into ways to potentially reducing the mass of our rocket in the future in order to increase the ratio. Next slide, please. All right, so these are two out of many relevant simulations that we run on OpenRocket. So on the left, you can see the angle of attack versus the time graph, and it's pretty stable. It kind of hovers around 0 degrees. And on the right, you can see the thrust curve of our motor and has the maximum thrust of around 1700 newtons. Next slide.
All right. As John had mentioned earlier, we inherited our hardware, our Aerostructure from last year's Phobos team, and because of this, we've had some unique challenges. As you can see, it's it has a very large diameter of 8 inches, which leads us to some design choices, such as using U-bolts for our parachute mounts instead of I-bolts, which basically reduces the moment arm on the bulkheads. In addition to that, it also has a very large cross-sectional area, so getting to altitude is a little bit more difficult. But for the rest of the rocket, we'll see two bays for parachutes between the leftmost, the payload bulkheads, and the center E-bay bulkheads. And then it'll be deployed with the couplers and the nose cone will be mounted with shear screws that'll be broken upon deployment for our drogue and main parachutes. Moving forward, what we'd like to do up until the end of the semester is get a solid design for the avionics bay to mount our components to fit in between the avionics bay bulkheads. Decide the bulkhead mounting method as well as the material through some trade studies. Narrow down our fastening methods such as the runners that we have, our stringers that we have running between our bulkheads, as well as just our general fastening hardware. We'd also like to do nose cone computational fluid dynamics analysis to narrow down our drag coefficient, as well as to make sure everything's sound. As well as we'd also like to do bulkhead stress analysis to make sure our bulkhead's mounting method, as well as our bulkhead itself, can maintain both deployment forces and motor forces.
Hi, can you guys hear me? Is my mic working? Good. All right, awesome. My name is Jonathan Stucker. I'm the ground station control lead for this year's Deimos team. And so our team is responsible for developing a predictive landing software so we don't end up losing our rockets. And so this is going to take place with a Runge-Kutta integration for our thrust curve. So from this, we'll be making a 6 degree of freedom simulator just to predict the trajectory of our rocket in case of some kind of catastrophic failure with our system. In addition, we'll be working with libraries to interface with our radios, and we'll be doing data collection from all parts of our flight. So we've been working closely with our GitHub that John Martini started, and you can see that below. Can we go to the next slide, please? Thank you, sir. So the 6 degrees of freedom simulator, we're working with a paper developed by a British university that kind of did the exact same thing that you can see on the right. And again, we want to do this just in case of some kind of catastrophic failure of our system where, you know, we wouldn't be able to get our final data to go recover our rocket. In addition to this, we'll be getting really important data during the launch and just as it's going through its flight. Next slide, please. So this is kind of what we have so far. So we've proven that we can get a very accurate simulation with a Runge-Kutta method of integrating our thrust curve. And we get that thrust curve from experimental data that we've taken from online. In this case, you can see on the right that we have just a mock motor that we found and got data from. And you can see in the middle, that's an Excel spreadsheet where we plotted all of that data from that experimental data. And we use a 6th order polynomial regression on it in order to get an accurate curve. So we have an actual equation. And then we threw that into our simulator. And you can kind of see it on the right, but it comes very, very close at the very end there to our total impulse. Next slide, please. All right.
So essentially for our project budget for this fall, we basically have topped out at $595, and then in the future we are in the spring we are projecting to hit $2,450. Now, however, that is an estimation mainly based on how much money we can actually fabricate these parts for, and then the bulk of it's going to be with essentially buying the M-class motor, then also paying for the rocket registration due in March. So and then also we will be buying the flight systems, the recovery system, which is going to run us about $240, and that is a cost that we have paid in the past. So it's a lot of stuff we already know is going to be going into it. So and then here's the timeline, and essentially so this fall we have been mainly software oriented due to COVID and the policies put on the lab. So that's why we are mainly doing that first, and then we're basically planning on having the rocket actually built in the spring. So essentially software, and then building almost all of the basic parts in CAD, and then testing them using FEA, and then also CFD. And then in the spring, we will be actually building and then also testing the whole rocket hand system. Questions?